So let's continue from yesterday. So all parts of the electromagnetic spectrum travel at the same speed. And again, we're assuming a vacuum. Therefore, wavelength and frequency have an indirect relationship. This means as one characteristic changes, the other changes too. Specifically, as one increases, the other decreases because it's indirect. Indirect means that as one increases, the other decreases, or vice versa. So as the wavelength of an EM wave increases, correspondingly the frequency will decrease. I got to pass. So as wavelength decreases, frequency will do what? Increase. So there's another fundamental thing that's more important in this class is energy. Electromagnetic waves carry energies. So short wavelengths have high frequencies. Long wavelengths have low frequencies. Energy is more associated with frequency. The higher the frequency, the higher the energy. Low frequencies have low energy. Correspondingly, we can combine these two things. That means that longer wavelengths have low energy, and shorter wavelengths have high energy. So, let's complete this table. If the wavelength is long, then the frequency will be what? It'll be low. And the energy will thus be low also. If the frequency is high, then the wavelength will be short and the energy will be high. So going left to right, it should be long, low, and low. And the bottom row should be short, high, and high. So here's a nice diagram of wavelength. We can see that radio waves have the longest wavelength. Again, the wavelength can be thought of as the distance between one crest to another crest. As we move left to right, the wavelength decreases. So from order of increasing or decreasing wavelength, we have radio with the lowest, our shortest, our longest wavelength, then microwaves, then infrared, then visible, then ultraviolet, then X-ray, then gamma. Gamma rays have the shortest wavelength, We can also visualize frequency from this. Frequency is how fast something bounces up and down in a given amount of time. We can see radio waves. It takes a long time for it to go up and down. But if we look at gamma rays, you can see how bunched up it is. A radio wave is can be on the order of 10 to the 3, which is 1,000. So that could be 1,000 or 1 whole kilometer, 1.6 something miles. Oh, yeah. No, I have that backwards. 1 mile is equal to 1.6 kilometers. So, a little over half a mile. Anything even longer than this is all considered radio waves. So, from about a meter, so anything about the distance of this meter stick to anything longer is the actual wavelength of radio waves. Microwaves are on the order of centimeters. We saw that the microwave from microwave ovens is about 12 and a quarter centimeters long, or 0.12 something meters. Infrared, I'll actually go to the next slide. Everyone good? So, smaller wavelengths as you go to the right, increasing frequency, and increasing energy. So as you go from radio to gamma, you're getting smaller wavelengths, your frequency is increasing, and the energy is increasing. And this is the order I memorize them. I always start with radio waves and move to gamma rays like this. It's the order of increasing energy or in frequency. So radio waves are about the same size as buildings and humans. Microwaves are on about the same size as humans and honeybees in centimeters. Infrared is closer to a pinpoint. So infrared is on the same order as the head of a pin, very small. Visible light. The wavelength of visible light is on the size of cells. Ultraviolet and X-rays are about the same size as molecules and atoms, so very tiny. Gamma rays are so short that their wavelength is on the size of atomic nuclei. So the distance between one crest and another crest, about the width of a nucleus. So very tiny. Visible light is about the same size as cells. I'll try printing this out and giving y'all a copy of this. We're not going to cover this in chemistry class, but do y'all know that everything glows? If you were in a dark room, you would actually be glowing. Do y'all know what color y'all glow at? Can you see someone in the dark glowing? Not glowing. So that tells you it's not visible light. If you can't see it, it can't be visible light. What temperature do you? What wavelength or EM wave do you think you glow at? So when you go out to the sun, you can get sunburned and damage yourself. What light does that? Ultraviolet. Ultraviolet. If we were glowing in ultraviolet, wouldn't we be destroying ourselves? It's infrared. Infrared. That's why infrared scopes. Yes. If you ever had an infrared camera, it's a camera that instead of detects visible light, it detects infrared. So you have a thermal scope. It's not really thermal. It's actually just a camera that views the world in infrared. That's because we all are emitting infrared light. Technically, anything around room temperature is glowing at infrared. As we increase the energy, remember temperature is average kinetic energy. As we increase the temperature of an object, we actually increase the amount of energy of light that's giving off by that object. So imagine you have inside your oven, you have a metal rod that looks black. It's actually glowing in infrared. As you start heating it up, some of the light emitted by it is going to transition into dark red. And it begins glowing dark red. As it starts getting hotter and hotter, it actually changes what light it emits. And then it'll turn into some infrared mixed with red and then oranges colors. And then as we continue to heat it up, it'll become bright orange and yellow. It'll be emitting red, orange, and yellow. And what happens when you shine all the colors in the rainbow together? It appears what color? What happens when you mix red, green, and blue? Like white. You're thinking paint. If you so how does your TVs work? They have a pixel that has only red, green, and blue lights. That's how your phone and TVs are. They have just 3 little tiny flashlights on them, and each pixel is just 3 flashlights: red, green, and blue. The color white doesn't exist. It's only an illusion in your mind. White is just a combination of all the colors. So when we say something is glowing white hot, we're saying that it's emitting all the colors. What color is the sun? What color is the sun? How old are y'all if y'all never went outside and saw the sun?
It looks white when you look at it from the ground.
How many of y'all think it's yellow? How many of y'all think it's white? Some of y'all are really uncomfortable.
It looks white.
Okay, have you ever had a yellow flashlight or a red flashlight or a blue flashlight? If you took a blue or red flashlight and shined it on a white piece of paper, what color would the paper look like? If you shined a red flashlight onto a white piece of paper, what color would it look like?
It'd be red.
It'd be red.
So the sun every color because we can see it.
So that means if the sun was yellow and I took this white piece of paper outside, it would be yellow.
Oh, so it's white because
it's white because it's reflecting the white light. The reason why it looks yellow, or people say it's yellow, is the only time you can really look at the sun without blinding yourself is during a sunset. During a sunset, the blue colors are dispersed more. And it's the reason why the sky is blue right now, is because you're seeing the white light is dispersing the blue more, making blue light fill more of the sky. But if you remove blue from white, you end up with a yellowish color. So what you're seeing is the fact that at sunset, when it's closer to the bottom, it has removed most of the blue light, and all that's left is red and green. Red and green mixed together is yellow. But during the day, like right now, you can look up at the clouds and see the clouds are white. Again, there is some blue light that's scattering up above, so it might have a yellowish tint, but that's light that's already been scattered. The sun is white. You can actually use this color to tell what temperature the sun is. So it's emitting the strongest color in the middle of the spectrum around green. You can actually say the sun is slightly greenish color. That's the strongest wavelength it's outputting. But it's also outputting large amounts of yellow and blue, large amounts of green, red and violet, just enough so that it all appears white when it reaches us, because you mix all the colors together, you get white. Around room temperature, it's infrared. And if you look at the scale Almost everything lower than room temperature is also infrared. This is the reason why. Has any of y'all ever parked y'all's vehicles halfway under a tree outside, and you get up in the morning in winter, and the part that's under the tree is not melted, and the part that's not under the tree is frozen. Or I say the one under the melting has no frost on it, and the one that's exposed to the elements is frozen. Have you ever seen that? Um, the reason that occurs is the sun is the tree is glowing in infrared, and that heat is being absorbed by whatever's closer to the sun, the tree. It's the only way that you can transfer heat in a vacuum or heat is by electromagnetic radiation, and you actually lose heat when you radiate infrared away. If you were to go into outer space, the only way you would cool off is actually by just radiating or glowing, because you're not touching anything. So let's look at the individual spectrums, or individual types of waves. Radio waves have low energy. They have the longest wavelengths, and is the reason why we use them in FM, AM, and radio and TV waves. It doesn't require that much energy to create radio waves. There are wavelengths of 1 meter and longer. Anything over a meter long or longer is most definitely considered a radio wave. They are low frequency and used in many devices such as remote control items such as cell phones, wireless devices, etc. Cell phones more get into microwave range, but it's weird because, like I said yesterday, sometimes they don't call sometimes they call microwaves still radio waves. Microwaves are considered radio waves are longer. Technically, that's wrong. Microwaves are radio waves that are shorter. They have a shorter wavelength. So, yeah, that needs to be corrected. They have a shorter wavelength than radio waves. Oh, I get what it's saying. It's saying only radio waves are longer than microwaves. So it's the next thing after radio waves. So it's the second longest wave. It's between a centimeter and a millimeter. A tenth of a millimeter. Used for communication, such as cell phones. Medicine and consumer use. Microwave ovens. Do you know the microwave oven actually uses, I always like saying it's a military grade magnetron. The microwave oven in your house is so powerful in producing microwaves, it is scary. Like, it was like the first product that consumers actually used that is like on par with the military technology. If you can take your microwave apart, you can build a maser. So laser is light, visible light. Maser is microwave light. And you can burn something like 100 feet away if you were to concentrate it. If you screw up ever so slightly, you kill yourself because you have to concentrate it to go in one direction and not all around a circle. And if you don't know what you're doing, you can most definitely expose yourself to high amounts of microwave radiation and cook your insides.
Doesn't sound that bad.
But if you do it correctly, you can actually burn wood, because wood has water in it, at very long distances. So it's a very, very powerful device. Infrared waves are invisible electromagnetic waves that are detected as heat. So again, electromagnetic waves are created by changing electrical fields. Changing electrical fields produce changing magnetic fields, and changing magnetic fields create changing electrical fields, and it makes it propagate out. Atoms. This is where we actually use the Bohr model to make it more easier to analyze. If you imagine the electron moving around in orbits, the fact that the electron is moving around is producing an electrical field, and because it's moving, it produces a changing electrical field. At one point, right close to where the electron is a strong electrical field, but as it moves away, that field decreases, so we have a changing thing. The fact that all atoms have moving electrons means that they all generate EM waves. Can be detected with special devices such as night goggles. Conversely, the fact that we emit infrared also means that we absorb infrared. So you've seen them heat lamps. All they are is lamps that produce a lot of infrared light. They're not very precise. They also produce a lot of red and orange light. Some visible light to them, but they mostly produce infrared. And your food can absorb the infrared and keep it warm. And conversely, have y'all ever seen an infrared heater? Space heater that's infrared? So they also have ceramic or quartz crystal ones, but they're pretty awesome. You can put one across the room and point it toward yourself and have the entire room freezing cold, but you'll be hot. The reason why is if you direct the infrared only pointing at you, only where the infrared light hits does it actually warm up. It's really great for outdoor uses because if you have a normal space heater, you're trying to heat up the air around you. The air, since you're outside, the air is going to rise up and it's never going to land on you. Conversely, do you know how fires heat y'all up? Have you ever stood next to a fire? How do you think a fire heats you up? So if you have a fire and you're standing next to it, there are two ways that that heat is transferred. Remember, temperature is the average kinetic energy of the molecules. So the air that is next to the fire, as soon as it hits a flame, will get a higher velocity. Because hot air is less dense than cold air, this hot air is going to go straight upward. So most of the heat from the fire actually flows upward. So a very small bubble around the fire with the air being heated, and all of it's going to go upward. You, however, will probably not feel any of the hot air. Instead, what you're feeling is the EM waves, the infrared light, actually shining on your skin. This is why if you stand next to a fire, your back isn't hot. Only the side that's actually facing the fire gets warm. Because if it was heating up the air, then it would be the same temperature in front of you as behind you. If the entire air was at the same temperature, then you wouldn't really notice the difference of the gradient in temperature. But if you stand next to a fire, you notice only one side of your body is actually getting warm. That is the actual physical light shining on you. So the only reason you get warmed by a fire is the fact that fire is producing light that actually hits your body. It's also why you can get warm by being somewhat farther away from a fire and still breathing in cool air. They're higher energy than microwaves, but lower than visible light. Visible light, the only portion of the light that humans can see. Their order goes Roy G. Biv. Red, orange, yellow, green, blue, indigo, and violet. And there are, of course, in between colors. Note, however, that do y'all know how our eyes work? This is a biology question. We have rods and cones. Rods only detect light amount, so they only see black and white. When you're in a very dark room, you'll notice you can't see color too well. That's your rods mainly working. Your rods actually extend more outwards, so your perception on the right and left is more using rods. We also have 3 types of cones. One cone detects red colors very well. One cone detects green colors very well, and one color detects blue. Let's see if I can find it good. All right, so we have 3 cones. If some blue light were to shine on your retina, then your blue cone, the one with the shortest wavelength, will activate the visual neurons more strongly. Your green and red cones will barely activate. If you get something that's green, this medium cone will activate more than this other one. If you get something orange, these 2 cones will activate very strongly, but the red one or the longer one will activate. But my point is, when a photon of light strikes your retina or your cones, a various combination of these cones will fire neurons in your brain. Your brain interprets color distinct from reality. For example, where is purple on this? What color is purple?
Well, purple is a mix of red and blue.
Yes. Red and blue together. If we look over here, so we usually say indigo looks purplish. That's because if we shine indigo right here, notice that there's a little bit of red right here and a lot of blue. If we were to continue moving over and shine both of them, our brain just invents a new color and we call it purple. Purple does not exist in real life, or in the EM spectrum. Neither does white. White doesn't exist. Black doesn't exist. The only colors we have are these colors that you see right here in this background. Combinations of color or brain events new colors for them. So the combination of red and blue is the fictitious color purple. It's real to us. In our brain, we see purple. It's just a color combination of both of these. You can never find a purple laser because there's no way of producing purple light that's only one wavelength. Likewise, there's no way to produce a white laser because white is a combination of all the colors. So if you were to start from infrared, after infrared, red is the first color. Then it goes orange, yellow, green, blue, indigo, then violet, and right next to violet would be ultraviolet. So which of these colors has the lowest frequency? Well, to help you out, which has lower frequency? Infrared or ultraviolet?
Would it be red?
Yes, red has the lowest frequency.
It took me a second. Yeah, what was where?
So if you were to squeeze Roy G. Biv in, this is the correct order of increasing frequency. Violet has the highest. So you see they're squeezed in here. By the way, this visible light is very, very small, narrow range. We only see the most tiniest sliver of electromagnetic rays. Some animals actually can see in ultraviolet. For example, bumblebees can see ultraviolet very well. Some creatures can see in infrared, which means they can actually see heat. Think like rattlesnakes can, maybe. Not entirely sure which. I don't think any people can see in ultraviolet. Maybe a little bit. There are some people who are born with 4 cones instead of 3, and can see a whole lot stronger color range. Which have y'all ever heard of that? Where you have extra cone and you can see multiple or different colors. I heard it's very frustrating for the people who have it because all of their clothing looks mismatched. Like 2 shades of color that is red to us, like there's no possible way people with 3 cone cells can tell a difference. They see it, well, this is way different than that color.
So how does someone be colorblind?
Colorblind, so you can be born with 2 types of cones, like red and blue cones. In which case you're missing the green cone. Another thing, going back to that curve, you saw how close green and red were. If both of them were perfectly overlapping, you wouldn't be able to tell the difference between red and green.
So that's why it's 3 times colorblind.
Yes. So some people are born with only 1 cone, in which case they see the entire world as shades of gray. Their gray might be all shades of blue, might be all shades of red to them. We don't. First of all, we don't know we don't know that the same color red I'm seeing is the same color red each of y'all are seeing. My red could be your green. My blue could be your blue. Again, our individual brains make up colors. Is how you interpret the world. None of it's real.
But I don't know. I kind of feel like we do see at least similar shapes.
I think so too, but there's no evidence to support that other than it makes sense for everyone to be able to look out for it.
It's like the emotional descriptions that you use like in literature.
That's what. So your emotional descriptions is funny. So red, or I should say pink. Pink, is that feminine or masculine?
I think it can go either way, but that's just like I don't think it should be feminized if you wear
really
pink, but I think it is more
generally
feminine.
like
light blue, feminine or masculine?
Either one. I don't think so. There should be.
So until about the 1920s, pink. So for hundreds of years, pink was very strongly masculine. Reason why is fire is red. Reddish colors were considered more masculine. Blood is red. So from war, people going out and getting all bloodied, coming back with your shirt full of blood was considered a masculine thing for some reason. And so red and pink. Pink was the thing you would give. Babies who were born male were put in pink clothing, and for some reason it flipped around the 1920s, 1930s, somewhere around 100 years ago. It flipped, and it always. I get a kick out of the people who are saying, you shouldn't put him in a pink shirt or light blue. It confuses people. I'm like, that's feminine. You're messing up his gender identity. And I'm over here, I'm like, hundreds and hundreds of years.
yeah,
Color's color to me.
it doesn't matter, but like you see
Like, I wear
most people.
And then light blue was associated with the water and soothing, nature, calm, which make no sense anyway. Oh, the sky too. So we're moving now into the higher energy wavelength. So ultraviolet has higher energy. They actually have high enough energy that when they strike an electron, it can actually cause the electron to fly off the atom, which can then cause chemistry to go on in your skin. Maybe it strikes an electron off of your DNA, which causes some of your DNA to fall apart, because once it removes the electron, it can do some reactions and can cause cancer, rewrite your DNA. So ultraviolet is the starting point where light can actually damage you, do chemistry. So you can get cancer from going into the sun. Again, it's statistical. Usually, whenever your DNA breaks down, our body recognizes it's broken, and we do one of two things: we destroy the cell, or we fix the DNA. Sometimes we can fix errors in DNA. Sometimes we just recognize it as bad, and we just tell the cell commit suicide. Sometimes the cell, if it does the correct thing and changes the gene that controls the rate of growth, the cell could start uncontrollably replicating itself. Usually certain cells split into two cells 8 times and then stop. Some cells start replicating uncontrollably, and that's known as cancer. X-rays have even higher energy. They're used in medicine, industry, and astronomy. They can cause cancer, and going into that is statistical. If you get hit with one deal of radiation, it can either go straight through you, it could damage the DNA, and that damage could be in a section of DNA that does nothing, like some bit of ancient DNA. I think we share 50% of the DNA with bananas, in case you didn't know. So as you can imagine, a lot of the DNA is not entirely that useful. I mean, it is kind of to some degree. Some of it's very common. There's a lot of repeating DNA, so that we can prevent errors from going on. But what gets dangerous is if you hit yourself with a lot of radiation, and we have like 1 billion cells that get have their DNA changed. Now we're talking about all it takes is one cell to become cancerous to uncontrollably replicate to form cancer. So just like light coming through that window, some light can pass through it. It's transparent. X-rays are transparent to flesh and muscle, but it gets absorbed by calcium in your bones. So whenever it hits your bones, it gets absorbed and doesn't pass straight through it. We can use that to take pictures. It's the reason why taking an X-ray also, it's alright to receive an X-ray, but as long as you don't take an X-ray every single day for a year, chances are one X-ray is definitely not going to do anything to you. Statistically, it's unlikely. And even if you do get one cell turned into cancer, usually the body can kill and recognize the cancer cell early. And usually it's not that problem. You probably had cancer multiple times in your life. Your body has just said, "Hey, this is not right," and goes and kills it. It's when it gets into a big enough mass that your body no longer is able to control it. It can't get into the inside of the cancer group or cluster to kill all the cells. After that, we have gamma rays, highest amount of energy, blocked from Earth's surface because it has such a short wavelength, it can't penetrate through the atmosphere that well. Luckily, we use gamma rays actually to kill cancer cells. If we take multiple gamma lasers, and have it pinpoint a single cell, we can basically make that cell explode, killing it. What we usually do is we give a dye that attaches to the cancer cells, and we actually can use gamma rays and start killing the cluster of cancer cells. If we have some fluorescent dye, something that can be detected by MRI or CAT scan, and we go in and find all the glowing cells because we added a fluorescent dye to them and attack them. So they're used in medicine to kill, and they're very powerful. It can obliterate. You can think of what lasers can do. That uses visible light. Gamma rays are way stronger. Let's see. So what's the relationship between frequency and wavelength? As frequency increases, wavelength decreases. The thing that gives gamma rays their high energy is due to their high frequency. It takes a lot of energy to make the waves oscillate up and down. Roy G. Biv is an acronym for, actually it's an acronym for the colors. Visible light. What color is more energetic, red or yellow? Yellow. So I just like remembering the order, Roy G. Biv, and then putting in infrared and ultraviolet. I know that anything closer to ultraviolet has higher frequency, higher energy, and shorter wavelength. And yellow is closer to the ultraviolet. Which type of wave travels faster, a gamma ray or a radio wave? The same. Again, for all purposes, we live in a vacuum. Thus, all light travels at the same speed. Why are microwaves more dangerous than radio waves? They have more energy. So you've just been involved in a traffic incident that leaves you stranded on the side of the road. Which part of the electromagnetic spectrum would be the most use to you and why?
Visible color. Invisible light.
Alright, trying to flag someone down. Deep East Texas, I wouldn't rely on it. I'd rely on radio / whatever cell phones use. But if you're out,
the service is kind of suspect.
But yeah, if you're really out here,
Just turn the blinkers on, maybe.
Visible light would be put your caution lights on, which would be visible light. Frequency and wavelength, the properties of waves, and since speed is constant for EM waves, as frequency increases, wavelength decreases. In other words, they have indirect relationship. They get their energy from extremely short wavelengths or extremely fast frequency. Yellow is more energetic than red. Gamma waves and radio waves travel at the same speed. Microwaves are more dangerous than radio waves because they have a higher frequency and carry more energy. And it didn't give the answer for the last one. I would say the last one, it depends. Personal though. As long as you explain a reason. Tomorrow, I'll pass out a worksheet for y'all to start working on. And then Friday, we will start actually doing equations with it, solving for the frequency and wavelength of various waves. And then next week we'll go in the lab and actually show why this is important for chemistry. By the way, street lamps, they're what color usually?
Is it yellow or?
Orange is yellow.
Yeah.
They're called sodium fluorescent lights. Do you know that is a single frequency of light? It's only one frequency. So if you're under a street lamp, every single color you see is the exact same color. If the only light is there is that street lamp. Every color is, your brain again can fill in the gaps. Oh, here, let me show you this. Let me show you how bad your brain deals with color. Alright, this color here and this color here. What color is this color? What color is this color? Are you sure?
Well, it looks brown.
So let me copy and move this over. Sorry, I'm on a touchpad. So there's that color. And let me copy and move this color.
Doesn't look orange anymore. What? Now they both look brown.
So, your brain completely reinterprets the things your eye sees. Everything in your vision is entirely constructed in your brain. Your entire vision is a lie.
So a lot of myself happening.